If people,
I think it should work now.
if people want to ask any question, I only have one screen, so I'm not going to be looking at the chat. But they can
I'll
ask
try to
me
look at
on
the
the
chat
reading group
and tell you.
or that. Sure.
Yeah. Let me check first that the stream is working.
Yeah, for the people in the reading group, and there are almost nobody people that are going to watch the recording. Yeah, you got the snoop that the scoop that yeah, there's going to be like kind of an official implementation from Anthropic that's open source. A bunch of different people are releasing it, both transcoders and cross-layer transcoders as well soon, and so that's going to be nice for people to be able to use them, and there's going to be like an I think like a Neuronpedia kind of plugin for people to play with them as well. Okay, I don't
People
think
should
anybody
be
else.
watching the recordings here to get all the news.
Okay, so I don't think anybody else is coming, so I think I'm going to start. So for the people that were not here last time, or the ones that were here, you're going to listen to this again. The idea that, like, one of the biggest ideas that Anthropic is discussing on this most recent work is to use what they call cross-layer transcoders to do circuit tracing. If people are familiar, this idea is kind of similar to something that some marks are done already, and also some people mentored by Neil, where you take in the case of some marks, you take SAEs trained on the residual stream, on the output of attention and the output of the MLP, and you make circuits with that, the normal way that you make circuits, I think, which is very similar to what Anthropic does here, which we are going to cover. In the case of the transcoder circuit paper, they don't do residual stream SAEs or attention SAEs. They instead just substitute the MLP with the transcoder, and they freeze the model to try to linearize it, and we'll discuss what that means. But they linearize the model, and they just trace the importance of each feature of the transcoder to the output, making circuits. This is, for those familiar, I think very similar to what we have already been doing, like with neurons, etc. And like the reason why maybe this is such a big deal is that yeah, maybe transcoders are a bit more interpretable doing this. Like, you get graphs that are much smaller with much less nodes than if you do it with neurons, while still recovering a good part of the performance. And the other advantage, or the other novelty on this, was really the introduction of cross-layer transcoders, which seem to be able to reconstruct the model performance better, while using the same amount or a smaller amount of active features at any given time. So to start, I already we are already looking at this image, but for those that are not familiar, the idea of a cross-layer transcoder is that you have a model which has some layers, and in each layer there's an MLP, and at each layer you're substituting the MLP with a normal transcoder that just reads from the input of the MLP and writes the output of the MLP, but also for all layers after the first one, the previous transcoder also writes to that layer. So in this case, on layer 2, this MLP is reconstructed by its own layer transcoder, but also by the previous layer transcoder. And while the activations of this CLT are defined just by a single encoder, so this CLT has an encoder, this CLT has an encoder, this CLT has an encoder, and this encoder reads only from the MLP input. Each CLT has a different decoder depending on the layer that it is writing on. So this CLT would read from this, and with one decoder will write to layer 1, with a different decoder will write to layer 2, and with a different decoder it will write to layer 3. In the case of Anthropic, they use jump ReLU to decide which of the features are active, and they train it with the normal reconstruction loss, MSE loss, but they also have a sparsity penalty that tries to minimize the sum. Like basically, you try to minimize the total amount of latents. Sorry, of latents across all layers together. This means that across the model, you'll have a distribution of how many features are active per token.
You train the transcoders in reconstruction, like all of the transcoders are trained with the reconstruction loss for all of the layers, or at least the layers that are after that the layer transcoder is on, right?
Yeah. So this CLT will receive gradients also from this reconstruction and from this reconstruction because it contributes to this reconstruction. Like the YL, which is the output of the MLP at layer L, is the sum of the activations of all previous layers times the decoder of all previous layers.
Okay,
so you have the reconstruction will have all the terms beforehand.
Yes, the first one is trained on all to reconstruct all of the layers.
Yes, the first one will output to all layers. Yes. And it decides that it's going to write to all layers just by reading the first layer. So the encoder reads the first layer and it will write to all layers, but the decoders will be different.
Yeah, it has a bunch of decoders. Okay.
Yes. And so
Gonzalo?
yeah.
Are you going to talk about the sparsity loss more? Because I've seen L1 penalties, and I thought this was really interesting that they have this 10H now. I don't know if people started doing that, and I only just found out.
I think they've done 10H sparsity penalties before. To be honest, I'm too dumb to understand this sparsity penalty. Like I don't quite understand. Like, I mean, I don't have any intuition why it would have this shape, or why it is better. If you want to, if you have any comment.
I have an intuition I can share. So if if you have no sparsity penalty, okay, and you build some kind of autoencoder where the dimensionality in the middle is higher, then it can get zero loss by just actually copying all the inputs with just an identity and then having zero for all the extra nodes, right? So what we really want it to do is to find these concept directions such that the number of non-zero values will be as low as possible on any given, activation. Okay. So if the residual stream is, dimension, whatever, 16,000, you want fewer than 16,000 activations at once, presumably. So what you really want is an L0 penalty.
Yeah.
Okay. But L0 is not differentiable, so we use an L1 penalty. tanh within a certain region imitates an L0 penalty because it doesn't keep going up and up like L1. It's just either 1, close to 1 for large values, right? Or 0, -1, whatever, for other values. And so it acts a little bit more like a binary penalty.
Right.
But
It's
it's
like
differentiable.
It's like a smooth step function.
Yeah. So I think that's what it is you want an L0 step function, but this is a smooth version of it.
Yeah, sorry. I meant to say that. I have intuition on why you want sparsity. What I meant to say is that I don't understand. It's not obvious. Well, it's not obvious, but they also do this summation over the layers. So they're which I think is interesting. So they're not only making each individual transcoder sparse, but they're constraining all of them to minimize their sparsity. So they're trying to minimize their sparsity together, which is interesting. Like that they link them together. Like you could still have this sparsity loss. Well, in the case of the top K, you can just do top K over each layer. But in their case, it's like they're doing top K across the layers as well.
Yeah.
Or concatenating all together and then doing top K.
Are you familiar with the diagram in the October 24 post? I found that to be really helpful. The top one under October. So if you scroll down a little bit, this one right there, just up a little bit, these two that are on your screen go together. So they say that because of the residual stream, actually your sparse features could be spread over different layer MLPs.
Yeah.
And so down below, the one that's still on your screen, but below where you see the two of them fused together, that's the the penalty that they're really trying to implement with, I think, the extra summation.
Yeah. I think that's the logic as well. And it's interesting they don't discuss it here. I think at least I didn't see any of these plots. But
no, that's why I was wondering if you were going to spend more time. I didn't see it.
Yeah, like one thing that I know people are doing is that you can look at the distribution of sparsity across layers, and you'll have something that's not homogeneous, but instead, like you have a spike on the earlier layers, and then it goes down, and then it goes up again on the later layers. But I think it's probably too noisy to have any kind of meaning for that. But I think you can probably maybe decompose that into different feature groups and try to see like meaning of different parts of the model, I think.
Yeah. Yeah, I don't know that it would be worth taking the time to do it, but I would. My intuition is that if you have communication across layers, that they'll be near each other, that you're really never going to have layer 1 combining with layer 20 to form a feature.
Mm-hmm. Mm-hmm. Yeah.
All right, thank you.
Yeah, so after you have this CLT model, if your reconstruction loss was perfect, which it never is, if it was perfect, you could just put it instead of the MLP. And now you have something that just fires very sparsely, and hopefully all the features are interpretable, so you could just trace the computation very well. Sadly, that's not exactly the case, and I think that this plot is a very nice way to look at it. So here they're plotting the different sizes of cross-layer transcoders per layer transcoders, and the idea of thresholding neurons until you have just a certain number of neurons that are active. And I can explain that a bit better later. But here in this plot you see that even if you use a cross-layer transcoder, where in total you have 10 million latents, when you substitute these cross-layer transcoders, your MLPs by these cross-layer transcoders, you still get that half of the time your top prediction will be different from the top prediction from the base model. And like this is just a very, let's say, fine-grained way to look at KL divergence, but gives you a number that's easier to think about. Like if this was like question answer, if this was measured in a question answering context, like this would mean that it would flip the answer half of the time, which seems bad. Obviously, if probably in that context, this fraction of incorrect would be a bit different. Here they're measuring this over like the full distribution, like the normal distribution, and there's much more options than just like 4 or 2. But indeed, changing the top token that much means that the model is performing different. It's not the same model. You're not reconstructing perfectly the behavior. And what this plot is showing is that even the smaller cross-layer transcoders are competitive with the bigger per-layer transcoders. And they, let's say, it seems like they maybe perform a little bit better. Like the jump from 300k to 10 million is wider than from 300k to 10 million on the per-layer transcoder. And on the other hand, here, this line of neurons, the idea is that this line, for me, it's very weird that it actually doesn't go to 0. But like eventually, if you don't threshold neurons, obviously, you'll just have the same prediction of the base model. But they say, okay, if you threshold it at this L0, so if your neurons, if only 10,000 neurons are active at any given time, they start to be interpretable, but you see that you get a very high error rate, much worse than transcoders. So like the argument could be, okay, maybe you can just do this replacement with neurons that were thresholded, but they're only interpretable after this above this threshold, and here there's already transcoders that are better and CLTs that are much better. This plot, the KL divergence is just the same thing as here. The scaling is a bit different, but the idea is the same. So here they're showing, okay, cross-layer transcoders are worth it because they're better than transcoders. Even though cross-layer transcoders have more parameters than transcoders, because even though they have the same number of encoder parameters, they have one decoder per layer. So you end up having, I think they say, n divided by 2 more decoder parameters, right? Something like that. Where is it? Yeah, you have n layers divided by 2 more decoder parameters and flops. So they train slower, but because even smaller cross-layer transcoders are better than bigger transcoders, you can probably make a trade-off and not make the biggest transcoder and still end up with a better replacement model. And so now that you have a replacement model, what do you do? The idea is that you substitute your neurons with the active features, and you first run through the model a fixed prompt, as whatever the prompt is. You collect the activation patterns and the normalization from layer norm or whatever kind of norm that your model has, and you compute the activations of all your all the layers of your CLT, and compute the error between the true MLP and the reconstructed CLT. And so you store all of this. So you store the attention patterns, the normalization denominators, and the error. And now you can try to make a graph that goes only through the features that are active. And if you freeze the attention, and by having the error nodes, because you computed the error, you are able to just compute the direct contribution. Like you can do attribution of how much each feature matters for the output, and how much each feature matters for the next output. Freezing attention is important. They still use, they still compute I always forget the OV circuit, but they freeze the attention pattern. I think this is explained here. I'm going to be honest, it took me a long time to actually understand what's happening here, and they have they have an appendix that explains like the exact maths. But the idea is that you're kind of tracing the gradient of you have a node that's your output, your candidate token, and for each candidate token that you want to trace, you make all the possible paths through all the features, and then to the input, and yeah, you just compute gradients, and these gradients will tell you how much each of the nodes contributes to the output. And I think they have, so they have, at the end you'll get something like this. Does the zooming in work? Yeah. Opa. Oops, sorry. Yeah. So at the end you have something like this, where this is already this is already a pruned graph. So if you have, this is your input prompt, which has 1, 2, 3, 4, 5, 6, 7, 8 tokens. Per token, per layer, you will have as many latents are active on per layer, which, as we saw, because it's a jump value, it's not a constant number, but it's going to fluctuate. I think the ones that they're using across like the sum over all layers, there's around 100 to 200 active latents. And so you'll have 200 active latents per token, but not all of these latents are as important for the final contribution, which for the final output, which in this case is DAG. And by tracing the gradient, so from this output, you see that there's all these different nodes, which I'm just going down, and these are the nodes that matter the most for the output. And you see that they're distributed all around the graph. Most of them are features that activate on the token N, but some of them you will see, like this one, activates on the token digital, and you'll see that each feature has this label. For instance, say G, say DA, say DAG, and these labels are made. Man, why are browsers like this? And I already. Whoop. Yeah, these labels were made by manually looking at activations. So this say G feature here, you'll see that in principle, the idea would be that afterwards there's like some words that have G's. You see AG, IG, IG, G, EG, PGA, LG, whatever. And they made these labels manually. They say that it's possible. So this one is called just digital because it activates on digital. Some of these, you see, for instance, this SAD. If you look at the top logits, most of the top logits start with D as well. And so the idea is that after you have this graph, you can group your features. So you can have you have 5 features, AD features, like all of these. The top logits are going to be words with D, and all the activating examples are going to contain the D after the activating token. And so you can make this very simplified and pretty graph with many less nodes than this graph, because you just coalesce them into what they call supergroups. And then the idea, after you have these graphs, is that you could potentially, and this doesn't work in this interface, but you could potentially kill some of these nodes and see how much the output changes. And hopefully, if your graph is actually computing anything real about what the model is doing, disconnecting these nodes or changing the nodes with some other values would change the output. I think this is okay. This understanding and labeling features was what I just described. I don't know if we want to read this, but the idea, one interesting idea, is that they find features that are just input features, which is they activate on digital, and no matter what comes next or before, they just activate on digital, and they're not really like predicting what's coming next, but maybe they are, because obviously digital, there's like it only represents some context, but it's mostly like an input feature. But they also talk about something that's an output feature. So you see that all these activations are, if you're just looking at the purple, it's maybe not obvious what the pattern is. There's some M's here, there's some A's here, some R's here. But if you look at the next token, it's always DAG. And so this would be an output feature. And in fact, if you look at the top predictions, it's DAG, dog, and then maybe it becomes less obvious. I don't know if we go to less activating examples. So now here you see in less activating examples, there's WEG as well. But for most of the distribution, you have DAG. So this is like an output feature. Then there's like output features which are not, let's say, as clean as the other one. Like it just the top predictions are just different types of sports. So it just promotes sports like football, netball, stuff like that. And yeah, and this one is the same as an input feature. It's just that it's not as simple as the other one above, which was just a digital, but it activates on all numbers that finish with a 6. So it's still an input feature. It's just that sometimes it's not. Input features are not single token. They have a pattern that can be interpretable. Yeah, these are just other kinds of features, but we don't really care about these. Again, grouping features into supernodes, this I think is a very interesting idea. I think people maybe when thinking about features like to think about them as independent things, especially because like the whole idea of like sparsity is that yeah, that if you have two features that are related, it makes if you're training the model to be sparse, you'd not want them to be active at the same time, because then your sparsity is higher, and so your model will try to specialize and make features for make one feature that contains the two somehow. But here they clearly show that for a bunch of features, for instance here, like in analytics, you have at least 4 features that are active at the same time on words that are similar to analytics, 4 features that are active at the same time on features that are similar, that are input features of digital, and even on, let's say, output features, you can have more than one active at the same time in most of the groups. So you say in this group there's even 5. Obviously these groups are not exhaustive, and they're very crude in the sense that if you look at the, let's say, the say-D feature, like it's hard to say that this is actually a say-D feature. So you see that after the most activating token, well, so there's the first activating token, then there's a second activation, and then D is active. But maybe, so in this case, I don't see like that there's any activation on G, or here on this C, there's no activation on C or in M. So this is definitely a say D after a bit, but it's not exactly say D. This one I think is even clearer. Like there's RD, idle, SIDA. So all of these are a bit more abstract, and they were made by a human, and that's why they look. It looks like the graph is very clean, but obviously there's some kind of like hidden mess. And yeah, what I was describing. Okay, now you have these graphs. How do you know if like this is actually related to how the model is doing anything? They talk about doing interventions. So you can just copy the normal activation that the model will have, right? You think that this node is important on your normal path. You save this, and you just add this feature on all the feature layers as it should be, but maybe you multiply by a certain number just to make it even stronger. And for instance, here they show that for this DAG example and DAG example, where the model has to find the acronym for this National Digital Analytics Group, if they kill the group feature, which because of that doesn't activate the say G feature, it makes the output change from DAG to just something that has they, other, them, then, they, DAG, which this feature kind of predicts that the model will say something about say da, but now there's no reason to say DAG because the G feature was suppressed. And I think they show here yeah, so if you inhibit each of these nodes, so if you kill digital, all the nodes that start with say something with D become much smaller, and in fact I guess this logic is just the correct answer is just DAG. It completely ruins the DAG prediction. If you kill analytics, you still influence a bit of the day, but the D, but you kill all the A's, and obviously DAG, and then the prediction. Instead, if you kill say D, you only make the BA node weaker. These ones are not connected directly, so they are not influenced. And interestingly, the logit node, even though the SEDA, the SEDAG feature is dead, you still have the correct prediction. I think that's what this logit means, that it doesn't, that the activity is still very close to the baseline. And yeah, some of these nodes, for instance, let's see if I can find. So you see some of these nodes, like these super nodes, like this say A feature, like super feature, is actually in 3 layers. You see, it's here, here, and here. These two are on the same layer, and I think this one is. So all of these are in different layers, but inside the same group you have different layers. All of these are going to be also in the same layer. Yeah. Right? Yeah. And so one thing that they're saying is, okay, can we find what are the layers that matter the most? And they just steer in different layers, and they see that yeah, there are some layers that it's important to steer, and steering works and makes the prediction wrong, but some features where if you just steer it later, it doesn't help that much.
Hey, Gonzalo?
Yeah.
Well, one other point on that is if the last analytics feature is on layer 12 that the CLT identified, then when you steer on 13, of course, it's going to have no effect because it already finished doing its work.
That's a good point. Yeah. Yeah. So if all the inputs, if all the input features that receive this analytics feature are after your intervention, they will not compute anything, and so your intervention doesn't do anything because it was already computed by the future features. That's a good point. And I think, yeah, this is what it kind of tries to demonstrate here. This is a case study that's basically the same, like the same thing, but now instead of DAG, it's using Michael Jordan plays a sport. Interestingly, this model only thinks with 60% certainty that he plays basketball. The rest is scattered through multiple tokens. The same thing here. I think, yeah, so there's this ablation case study, which I think we can look at. I don't know if people care about some of the CLT like details. For instance, the fact that the reconstruction loss is better for smaller L0s than the pre-layer transcoders. They also do some interpretability analysis where they show that for the same reconstruction loss, you can have, well, for better reconstruction loss, you can have more interpretable features, and by the way that they measure interpretability is with this sort eval and this contrastive eval. If you don't know what they are, they're a bit complicated to explain, and I don't quite understand why they care about. I think these evals are a bit hard to reason about. But basically, what they're claiming is that cross-layer transcoders are just better at reconstruction and better at being interpretable. In this case, by Claude. They also show that you need less. You can have shorter paths that contain more influence, and I think there's a new one, a different one. Yeah, that just shows that you can by having a smaller L0, your graphs are going to be more complete and more correct in this replacement score, which just measures the fraction. Just measures the fraction of information that goes from your embedding nodes to the logit nodes. If you just kept all possible nodes, you'd have 1 and 1, but obviously you want to have the highest number for both by having the least amount of possible nodes in the graph. They also talk about pruning. I think pruning is a bit of like a technical thing. If people want to read the implementation, they can. And I guess if you want, we can try understand this addition case study, where now here they don't look only at the graphs, but they also look at activations of features. For instance, if I'm understanding this correctly, this feature activates on numbers, on all numbers, strongly activates on all numbers between 50 and 60, even though it activates on all numbers more or less, while this one, the direct effect of the sum of a feature decoder on the output. Yeah, in this one, instead of being the activation of the feature, it's the logit length. So you take the decoder direction of that feature, and you see that it lights up on all numbers that are 5 modulo 10. I think that's how you interpret these graphs. So you see, for instance, this feature here, you see there's all of these activations on random tokens. But if you just look at the top tokens, most of them are like numbers from 90 to 99, and the bottom ones are 100, which is kind of what is represented here. This, on the other hand, really makes it sharp that it's 99, 95, like the top are all 95. This one is modulus 5, so this is kind of modulus 95, but you're only seeing from 0 to 100, so modulus 95 just activates on 95, and they see that there's these patterns for a bunch of different features. There's these lookup table features, which I don't quite understand the patterns. I think they show it here. They activate conditionally on this and this, and so they activate only on when both of them are true, which makes these grid patterns. Because here the numbers go from 1 to 9, so these are 9 squares, and the numbers go from 1 to 9 here as well. I don't know if people have read this and there's anything interesting here that they want to discuss. I like this. I think these patterns are very cool, but maybe I didn't explain them correctly. So if people want to say anything. Okay. So I was explaining something wrong. So they're actually looking at the activation on the equals sign of the. So this is they're looking at the features that are active on these, only on these equal. All these features are only active on the equal sign, and so the x here is the one of these numbers. The y is the other number, and they just run all possible tokens, and they see the activations, and you see that they activate mostly on this diagonal, which is going to be that the sum of these two numbers is close to 92. And in this case, it's precisely 92. In this case, it's modulus 5, and that's why it makes this pattern. In this case, it just sums to be around, it's just 40 plus 50, which can make all this blob, and all these shapes are the different. I don't understand this. This just means that doesn't matter what's here, it will always be 57, and this is the same, but 9 because it's modules. You were saying something?
Yeah, I was just going to say, my first reaction is this seems kind of inefficient and error prone. When you drill in, like on the sum is 95 one, you'll see that in the upper right corner, there's some stronger activations that are nowhere near 95. I think it's when you scroll up. But anyway, the point is on all of them, you'll see some things that are just like not really quite fitting the pattern. But then I kind of reminded myself that the LLM is, oh yeah, this one you see in that corner there. And then on the right, the add 9, you see it's mostly a strong vertical pattern, but there is some horizontal stuff at the bottom and on the right? But then I reminded myself that this model is not only doing addition. So maybe some of these other patterns that don't seem right to me maybe they help with multiplication or fractions or something else.
Yeah, in fact, you see that like the activation of the feature that when it is on an equals, it tries to sum. Like if it sees 36 plus 59, it tries to sum those numbers. But if you just look at this, you can see that it is active on a bunch of different features. Like it's active on these spaces where there's no sum here. There's no sum here, and so yeah, it's clearly doing something more than just summing 92, or at least otherwise the model is a bit confused and thinks that in this space somehow it must be summing something, which is obviously a strange meaning thing.
Yeah, I mean,
Yeah, that's right. Like it could be confused, but I think the more I thought about it, I'm going to give it credit for some sort of distributed computation, constructive interference, and that it's actually, you know, since it does get the right answer for all the 2-digit additions, this is probably helpful in some way. I just don't understand.
Yeah, I was wondering, like, how do they know? Like, I think in this example, it's pretty clear, but how do they know when the model is doing something on purpose versus when the model is like doing something or it's trying to do one thing, but it's accidentally, in some cases, doing the other thing? Like with the sum 95 features in that upper right corner, like, could that be interference? Like, how can they tell between the models? Like, or can the model even be said to have like intentions to what it's meant to implement? Like, I don't know.
For me, the answer is, is that you don't know. At least we are not even close to like being able to answer that question. I don't know if other people have opinions.
I mean, in this case, you have the model and you ask it a math question and it gets the correct answer. I think it makes perfect sense to like consider that it's in some sense it's trying to output the correct number to the math question because it was trying to output the correct number to the math question.
Yeah, so I definitely, yeah, I think that's a valid question. In the like thinking about, is this actually a sum 92 feature, something like that, it becomes clear or clearer that in this specific context where you're doing sums, it is probably a sum 92 feature, but it's still probably doing much more things. And there's like, we still haven't found like the clean decomposition that people have been waiting, especially with like SAEs, because in different contexts it seems to be doing something else. Like maybe, yeah, maybe if you're doing this task of speaking French with some numbers, you'd find a different circuit that would be very clear what it is doing. Even though it's weird that it would be that, because obviously the topologies are numbers, but maybe it's doing something about dates or whatever. But if this is the real ontology of the model, I think it's very hard to say something. I don't know if that was kind of your question or not.
Yeah, I think that was a pretty good response. I think it's just hard. Yeah.
Yeah. Yeah. So we are already at 7. The rest is more. So this is a cool thing, I think, as well. So you can, yeah, you can just disable some of the feature nodes, and this impacts like future things. Like obviously, if the model doesn't know that it's adding stuff, then it cannot know that the sum is a certain value. So even if this is not the correct ontology or something, it is definitely like an approximation of the pathway of information going through the model. And like you can make the model basically say the wrong thing because you're summing the wrong number, right? So this is so the model predicts correctly that the answer is 95. If you instead suppress that the answer is not, that the sum is not 95, it will predict all numbers except 95. And then some others like 15 here and some early numbers. If instead you're summing 36 plus 50, it somehow still gets 95, but on the wrong place. If instead you say something like 59 plus 30, it also somehow gets 90, but on the other side, maybe some smarter people will understand what's happening here. If you do both of these, it still gets to 90, but now it's a bit uncertain. And I guess it's because there's like this sum too close to 92, and you get like some smear here. Like global weights, we don't have time, and I didn't read. If someone understands and wants to write something on the chat, they can. Then I think after that, it's mostly like more like problems about this approach, which I think is a valid thing to read, and it's probably the most important thing to read. But yeah, we don't have time, and I think we shouldn't do a third round of this, but instead should do something else. And if people have questions and want to discuss, now it's the time. Speak now or be silent forever.
One thing I was thinking about when reading this was, what's the cause of supernodes? Like, I wasn't clear if supernodes were nodes that activated like together at the same time or like separately. Because if they activate together at the same time, then obviously that's like a penalty. So like, why are we getting these nodes? It seems like it's obviously better to just for the model to merge them during training.
Yeah. So I tried to mention this, and I definitely I think that it's a very interesting phenomenon that it happens. So some of the times, well, in this case, because they couple, so for instance, here in digital, all of these are in the same layer and on the same token. So the model is penalized. But it could be that so for instance, you see this say D. So one of these features is on here, is on N, but another feature is here on the uppercase. So these two features, which they label the same thing, I already lost it. Yeah, this one and this one. They're part of the same group, but they're part of the same group, but they're on different tokens. So there's no penalty there. So here, kind of what the argument is that there's also like token superposition in terms of features. So you don't only have to worry about maybe layer superposition where the same feature is in multiple layers. And I think, you have it here. So this feature, this group is on different layers on the same token. So with their penalty, it would still better to just have one of these features. But that doesn't happen. I think what's happening is that, again, as we discussed with the summation, like this feature is probably has a bunch of different meanings, and we are just in this concept, it is about saying D. And when these three features are active, it does exactly that. But if other features are active, it does something else. And so it's like the combination of the features that's deciding what it does. Also, probably the combination of the downstream features, not only the ones that are active on the same token, but also some of the previous ones. And so, yeah, I think the answer to your question is that we are still not. There's probably no clean decomposition, and so models are not trying to learn a clean decomposition, and they learn like interactions between features to represent some behaviors.
So you mentioned how the model might be using co-activations. Like its meaning, the meaning of a feature might change depending on its activation. I thought about like, what if you somehow regular like add a penalty to encourage independence of features? Like you don't want features to be predictable from other features, but would that? I mean, that would obviously solve the problem of like features in the same layer predicting each other. But would that even be? I don't know. I don't know if that would still like meet all the criteria I expect.
I think that there's some people that have tried doing that, like trying to make a penalty for having like features be or more orthogonal between themselves. I don't know. I think even like to have less mutual information. I'm pretty sure. I think at the end of the day, most of them just make your reconstruction loss worse.
I mean, like there are some concepts that are not the same concept, but they are correlated. Like
yes,
if you
exactly. That's
make
also
that not happen, you are not going to reconstruct the model. If maybe that happens too often or something, it also could be okay. Like maybe it turns out a lot of this is just in this context the all of the features seem to be doing the same, but there is some other prompt where they do something subtly different or something, and maybe the correct thing to do is just have the different features and just you categorize which ones are important. They are doing more or less the same thing for your specific prompt. I don't know.
To me, this feels brittle. Like this feels like I don't know. Like if you want to generalize to multiple prompts, like you want to have an intervention that generalizes to multiple prompts, like it sounds like you're just accepting that this cannot happen because features are so subtle and we can't really understand them 100%.
Yes. So that's actually something that some people think about. I don't know. I don't know the opinion of Anthropic on this, and I would assume that they think that it's not as brittle. But yeah, the reason why they did these like case studies as in individual prompts instead of like in the circuit way where you just accumulate over a bunch of prompts and you average, is that yeah, probably this is all just too brittle, and there's not a universal circuit for a group of prompts even, and like circuits are just you can only trace like the information flow, but there's not a general like unique circuit for any behavior, and that's a bit sad. But yeah, it could mean that it doesn't exist at all, or maybe this whole decomposition is just the wrong way to do the composition, and so you'll never find it.
And also maybe maybe the the current transcoders are not that good, and you have some like even the same kind of thing, but just better lower reconstruction loss, you will get more sensical circuits or something. I just feel like maybe like they just the way they are dividing the model, like maybe there is you will need something else. I'm not sure what that looks like though, but it could also be like the sparsity penalty is not the best one, and there is some alternative, like slightly different formula that just works. But yeah.
So who's
Yeah,
working on open source replication of this?
yeah. So okay, that's a good question. We okay. I put it in the channel. We have working code that does graphs, and you can also just visualize them like the ones that they show in their paper. You have to have like to run the model yourself and have either the CLTs or the transcoders. And I don't think that there's any there's any public release that allows you to actually use this code. And we haven't we haven't made the announcement because we are still working on it. But yeah, people that are working, some fellows at Anthropic, like fellows are these like kind of intern program that they have, are reproducing it, and they're making it open source as well. Soon, like next week probably, and so people will be able to play with this. And yeah, the attribution code is easy actually. It's maybe harder to just train good transcoders and good CLTs. Yeah, I have to go. Sorry. It was nice, the discussion. I hope that it was not too boring, the overview. And yeah, we'll have to decide what we're talking about next week. I think I can guide the group again, but I'm not sure at the moment. I'll say something later.
Okay.
Thank you. Have a great week.
Yeah. Bye.
Good week.
Okay, I'll close the recording.